We all are here for the third Centenary Lecture under the Centenary Lecture series by our beloved alumnus, Professor Asok Kumar Mallik sir, on the topic An Hour with Leonhard Euler. This session is to be chaired by Professor Omit Roy Chaudhuri of Department of Aerospace Engineering and Applied Mechanics. Sir, I would request you to please take over the session.
Thank you, everybody. Very good afternoon. Actually, it is my great pleasure to be present here. And I am very much thankful to the organizer for inviting me in such an auspicious occasion. And also, I feel honored for it. I do not want to say much about the huge academic charisma of Professor A.K. Mallik, but I feel myself unfortunate in that sense that I could not be his class student. That is one point. But I feel fortunate that I have got him for last few years when he was in my department as a distinguished professor. Actually, I will say some personal interaction with him. It is really, what I will say, I feel fortunate that I have got such a finest mind. I have come closer to such a finest mind. Actually, whenever I interact with him, that is a huge pleasure for me. We used to, every time when I went to him and I used to discuss with him, I am thinking in this way, some value has been added to me. Actually, in different area we used to discuss. And regarding being a student of science, what should be my attitude to the science? How I should approach to a problem. And even if, what is the limitation of science? All these, because these are the very big aspects, but he has to give us the tidbits regarding this. And I am telling you, and regarding the innovation, discovery, he used to tell some story. From that, I can understand that it is not that the individual matters. Sometimes the social factors matter, historical factors matter. They are the driving force. From that, I come to understand that knowledge is also social. Individual matters, but knowledge is social. Means social driving force acts. So all these aspects I come to understand from him actually. That much I can say I must confess. And all of us, he does not need any introduction actually. But formally I have to say something regarding his academic achievement. He did his MTech and a B and ME from our Bengal Engineering College under Calcutta University. Then he did his PhD. He joined as a lecturer in the IIT Delhi and then IIT Kanpur, and he completed his PhD from IIT Kanpur, and he got different awards, numbers of awards and numbers of what I will say that fellow. He is also the INSA fellow. He got the Distinguished Teacher Award in the IIT Kanpur, and he also INAE fellow. So I must have to say that such a, what do we say, that pleasant and academic minded people I have met in my life a few, and he is one of them. Really, I am fortunate enough to be here, and also I will say that nobody can deny that personality, academic personality like Professor A.K. Mallik and myself is also graduated from our same department, that mechanical engineering department of Bengal Engineering College, Calcutta University. So I feel fortunate in this way. We can say many words about his academic achievement, but I will not longer my deliberation. I will request Dr. Mallik, Professor Mallik, to start his lecture. Thank you, sir. Professor Mallik.
Thank you, Amit, for making the embarrassing introduction short. And I would like to thank the organizers, especially Sudeep, Vidyut, and others for allowing me to join this function. Let me start with sharing with my slides. I hope the slide can be seen. Hello?
No, sir.
Not yet, sir.
Not yet, sir.
Is it not seen yet?
No, sir.
Can I start?
Slide is not visible.
It is not seen, sir. Why?
Slide is not visible.
Not visible, sir.
What happened? Just now we checked. Just now we checked and it worked. Is it seen now?
No, sir, not yet.
Not yet.
So, you have clicked. Yes, it's coming, sir.
Has it come?
Yes, sir.
Yes, yes, it's visible now.
Okay,
Sir.
now I get into the slide mode.
Yes, sir.
Can you see it now?
Yes, sir. Full slide.
Okay. Let me first tell you, why did I choose a mathematician to talk about in a centenary lecture on the occasion of mechanical engineering department? There are three reasons behind it. The first one is I am somewhat out of touch with mechanical engineering for a few years, so I'm not competent to talk about mechanical engineering. Number two, the first two lectures in the same series were excellent lectures, one on mechanical engineering and the other on general engineering profession and activity. So to avoid, stiff competition and unfavorable comparison, I decided to go on to a new track so that you cannot compare the previous lectures with mine. And I did choose Euler for a specific reason, because this is one mathematician which all mechanical engineers have met number of times, encountered number of times in various subjects. I will touch upon a little bit about Euler's life and achievement as a mathematician and test a few of Euler's typical mathematics. Leonhard Euler was born in 1707 and died in 1783. He was born in the city of Basel in Switzerland and died in the city of St. Petersburg in Russia, which was later on named Leningrad and again renamed recently as St. Petersburg. Life of Euler, the typical, you'd say, milestone events. 1707 he was born. 1720 he entered the University of Basel. His father, who was a clergyman, wanted Euler also to be a priest. So he started reading theology. But John Bernoulli, the father of Daniel Bernoulli, our famous Bernoulli equations, Daniel Bernoulli, his father John Bernoulli, who was great professor of Europe in mathematics, and he was at that time professor in Basel. So he noticed Euler's genius as in mathematics and convinced his father that he should study mathematics. Not only that, he even told Euler that every Saturday you can come in the afternoon with all your difficulties and questions and we will discuss mathematics. 1722, Euler graduated from Basel, and obviously there was no job for mathematicians those days, and he is hardly 15 years old, as you see. But John Bernoulli's two sons, Daniel and Nicholas, they somehow obtained professorship in Peter the Great Academy in St. Petersburg. So they invited Euler, who were friends with them, that why don't you come here and join? But there was no chair for mathematics professorship. So he had to join as a professor of physiology. But 1727, he earned the Paris Academy first prize. And 1727 to 1741, he spent in St. Petersburg as a mathematics professor because Nicholas Bernoulli, who invited him, died in the drowning process. So he got the Nicholas's chair in the mathematics. But by 1735, Euler was declared the best mathematician in Europe, that is, best mathematician in the world those days. And in 1741, when Frederick the King of Prussia opened the Berlin Academy, invited Euler to join his academy as the professor of mathematics. Not the director of the academy, but as the mathematics professor. So he joined there in 1741, but by 1766, he decided to leave Berlin because this king was not interested much in mathematics. He was more interested in philosophy, literature, music, classics. So he found Euler rather boring, that because Euler doesn't participate in all the philosophical discussions. In fact, when the queen said, "Mr. Euler, why don't you participate in the court discussion?" Euler said, "Madam, I come from a country where if you open your mouth, you lose your head." So 1766, he went back to St. Petersburg and died there in 1783. Note that he lost vision in one eye in 1735, when he was only 28 years old. And he became totally blind in year 1771. And last 12 years of his life, he did mathematics with total blindness. He had phenomenal memory, not only in mathematics, in all matters. He could recite, epic Aeneid, which was written by Roman poet Virgil, word for word. And mathematics was so natural to him that in his obituary, Condorcet wrote that he calculated just as men breathe, as eagles sustain themselves in the air. No effort is needed. That's what it means. In fact, while dictating mathematics to his scribes, his son was also one of his scribes, Euler, without vision, would go back 20 pages to correct something. He could have 20 pages of mathematics in his head. He would go back and correct it. He would do mathematics with children or grandchildren playing on his lap because it didn't require any extra effort. Once two students' disagreement on the fifth digit after the decimal point of the sum of 17 terms of a series was settled by Euler by carrying out the entire computation in his head. Just notice the things, fifth digit of the, after the decimal point of 17 terms of a series, and that he could calculate mentally. Euler was very productive in every word, sense of the word. He had 13 children with his first wife, who died in 1773. He married again in 1776, the cousin sister of his first wife. And out of his 13 children, only 5 grew to adulthood. All 8 died in the infancy. Only 3 sons outlived him, and 2 daughters died in the last year of his life due to the process of childbirth, which was the most common cause of death of the women folk in Europe. During his second stint at St. Petersburg, Euler was invited by the Tsarina, Catherine the Great, the Peter's wife, who called Euler back to St. Petersburg. that you have to convince the atheist French philosopher Diderot about the existence of God. Because Diderot, the French philosopher, came to St. Petersburg and was converting all young men to atheism, no God. So Queen got, concerned. And Euler had such a stature, he said, Euler, if he says this is proof, everybody has to accept that is proof. So the story goes like this, that Euler came to the court and said, with all the authority and fame of the greatest mathematician of Europe, he just said, a plus b to the power n by n equal to x, hence God exists. Obviously, this is mumbo jumbo. I don't think this is the truth. But the story itself tells what authority did he wield over the intellectual life of Europe. That Euler is the greatest, whatever he says must be accepted by everybody. In the 18th century, Euler was in the 18th century, and the 19th century French polymath Laplace, he said, read Euler, he is the master of us all. So another mathematician, German mathematician Frobenius, whose name we have heard in differential equation, he says Euler lacked only one thing to make him a perfect genius. He failed to be incomprehensible. It looks a little funny because actually Frobenius was not very happy with Gauss. Gauss used to write very little, and whatever he wrote was almost cryptic. Nobody else could follow. So when he was told, why don't you write it little more explicitly, Gauss said, you see, the scaffoldings are removed once the cathedral is made. The sculptor wants you to have in awe. So I also want to have you in awe in my mathematics. The way I reached it, I would like to remove it. And Euler was just the opposite. He was a great teacher and great author. In fact, he even wrote whenever he did go wrong, so that others don't commit the same mistake. In fact, there is a saying that Euler wrote 2 books, differential and integral calculus, and one person commented that he wished nobody else ever repeated a differential or integral calculus textbook. Then we would have read Euler's book. That is the best book possible. This is that they say Gauss and Euler, there's exactly opposite character. Gauss was the architect of cathedral, and Euler was the great teacher. Now, during Euler's age, there was no Nobel Prize or Fields Medal. Let us talk a little bit about his achievement. So every year, academy used to define an important problem. You cannot choose your own problem. The academy will decide what is the important problem for the society, which scientists should try to solve. And there was a very lucrative prize for the best solution. That was one way of earning some money for all scientists. And all over Europe, the greatest scientists used to join the competition, and the academy used to be the judge. And the first prize was given a very lucrative monetary incentive, and all inferior solutions were burned in front of the academy. Thank God this practice didn't continue, because now with so much of junk paper all over the world, there would have been, really air pollution. So much things had to be burned if inferior solutions have to be burned. The prize of the Paris Academy was most prestigious, and Euler received record 12 times this prize of the Paris Academy, and Daniel Bernoulli got 10 times. And this prize was so coveted that Daniel Bernoulli, in one of these 10 times, he had to share it with his father, John Bernoulli. And John Bernoulli, he came and told his father, Papa, we have got both the prize of the Paris Academy. Immediately, father turned him out of the house, said, how dare did you enter the competition knowing full well that I have entered a paper there? So that's what John Bernoulli. On the last day of his life, September 18, 1783, he had a normal day doing usual mathematics until 5 p.m. Then, while sipping a cup of tea and playing with a grandchild, he had a massive cerebral stroke and declared, I am dying. Unfortunately, like so many other mathematical conjecture of Euler, this conjecture also proved to be correct. He died at 11 p.m. the same night. Now let us have a little look about mathematics of Euler. In quality, it is obviously the highest quality. Diversity is mind-boggling in how many different number of fields he created and worked. And quantity is still unsurpassed. Nobody has done more mathematics than Euler. There is a magazine, Mathematics Intelligencer. They once conducted a vote asking all the present-day mathematicians that what, in their opinion, is the 10 most beautiful formulas in mathematics. Euler gets the first, second, and fifth position. Out of those 10, first, second, and fifth position was obtained by Euler. E to the power I pi plus 1 equal to 0, which all of we know. And other one is the number of vertices, faces, and edges of a convex polyhedra, which must satisfy V plus F minus E equal to 2. And number 5 was the summation of 1 upon n square, where n takes all the integer values, is pi square by 6. This sum was a great problem in Europe, and for more than a century, it was unsolved by greatest of mathematicians. So Euler solved it and immediately was considered the best in Europe. Let us look at the list of these 10 problems. As I said, the first one is e to the power I pi plus 1 equal to 0. Second one is the convex polyhedra, number of vertices, faces, and edges. And number 3 is the Euclid proof of infinitely many primes. That prime numbers are not limited, they continue forever. Euclid's proof, that is the place third. Fourth place is there are only 5 regular polyhedra. Greeks found it that there can be only 5 regular polyhedra. And number 5, as I said, is that Bessel problem, a sum of 1 upon n square is pi squared by 6. Number 6 is continuous mapping of a closed unit disk onto itself as a fixed point. Root 2 is irrational, that is the given by Euclid. Pi is a transcendental number, the proof was given by a German mathematician Lindemann. Number 9 is 4-color theorem, that any map, to draw any map to distinguish neighboring countries, 4 different colors are sufficient. This was known for quite some time and ultimately proved with the help of a computer in 1976. And then 10 is that every prime of the form 4n plus 1 is the sum of 2 squares in only one way. For example, if n is 3, so 3 into 4 plus 1, 13 is a prime number. And that prime number is 2 square plus 3 square. So it is a sum of 2 squares and in a unique way. Same is for 17, 1 plus 16. Or 41. 4 into 10 plus 1, 41 is 16 plus 25, 4 square plus 5 square. This was stated by Fermat, but the proof was given again by Euler. These are the 5 regular polygons, which I said the Platonic solids found by the Greeks. And you see tetrahedron, hexahedron, octahedron, dodecahedron, and icosahedron. And if you count the vertices, edges, and faces, in every case, you'll see this will come out to be 2. It must satisfy Euler's equation V minus E plus F must be equal to 2. After pi and E, the most famous mathematical constant is known as Euler's or Euler-Mascheroni constant. It comes from a very simple thing. We all know 1 plus 2 plus 3 up to n we can add. But if we take the reciprocal of these integers, can we add? Can we have a formula for Hn? It has been found no formula exists for Hn. But what is known that Hn does not converge. It continuously increases. That means it diverges. This is called harmonic series. And that the harmonic series diverges, the proof is very simple. It was given in the 13th century by Nicolas Oresme, French polymath. This series is called the harmonic series. It diverges very slowly. Now the question is, how slowly? So you see rate of divergence of Hn. If I take 100 terms, the sum is 5.187. If I take 1000, it is 7.486. If I take million, it is 14.392. So Euler wanted to find what is the rate of divergence of Hn. So what he noticed that if I take log of n for n equal to 100, 1000, and million, I get these. And if you take Hn minus log n, you get these numbers. You see they are sort of converging to 0.57 kind of thing. So what Euler did, he defined the difference of Hn minus log n as gamma n. And he first proved that this gamma n tends to a limit as n tends to infinity. This limit exists with n increasing. And that value gamma is called the Euler constant or Euler-Mascheroni constant. Actually, Mascheroni only calculated it to 20 decimal place, but it's really Euler's constant. And Euler constant, this gamma n, converges very slowly. Gamma n converges very slowly. For example, if you take 100 terms, the value of gamma is correct only to 1 decimal place. And if you take 1 million terms, then it is correct only to 5 decimal places. So Euler first calculated it to correct up to 6 decimal places, then correct up to 15 decimal places. So obviously he didn't write all these terms and add it. There is a huge amount of mathematics around this Euler's constant. There is a very nice book by Havil on this particular constant, Euler's constant. Later on, Soldner calculated up to 20 decimal place, Nicolai 40 decimal places. And when the computer came, great computer scientist and mathematician, Stanford professor Knuth, he calculated up to 1721 decimal places in 1962, computer primitive. In 1997, 1 million decimal places. So what I'm trying to say, that just like pi and e, this constant is of very much of interest for mathematicians because there is so much mathematics around it. And they have calculated even up to 108 million decimal places. Euler created many useful mathematical functions. All of us know about this gamma function, studied as undergraduate maths. Gamma n is this integral, which is n minus 1 into gamma n minus 1. So for n integer, I can see it will converge to n minus 1 factorial for n integer. So integer values of n, gamma n in factorial n minus 1. What Euler did, he used it in the reverse to define the factorial function for fraction or even negative. Because it is known the gamma of half, this integral with n equal to half is root pi. And gamma n is n minus 1 factorial. So I can say minus half factorial is square root of pi. Euler defined the factorial for negative and fractional numbers. Now let us look at the different fields where Euler worked. He worked in number theory, both elementary and analytic, that is using complex numbers, complex variables, algebra, geometry, combinatorics, analysis or calculus, infinite series, mechanics, optics, graph theory, and whatnot. Because this one slide is not sufficient to list all the fields. Actually, this is a famous problem of Euler, that in the city of Königsberg, there are 7 bridges across this Pregel River. You know, this river branches off in a funny way, and there are 7 bridges. So the citizens of this city couldn't figure it out whether it is possible to start from a point and return to the same point, crossing each bridge only once, whether it is true or not. So Euler was posed this question. He showed that no, it is not possible, and he was a little irritated that why a mathematician was required to answer this question, which demands only simple logic. It was so easy for Euler, but what he didn't realize that he gave birth to a new mathematical field, that is graph theory. Euler's printed mathematics runs into 25,000 pages. More than 866 papers and books. Opera Omnia, actually in 1911, Swiss Academy thought of publishing, rather editing and putting all the Euler's work together. They found it will require more than 70 volumes. By 2015, there are papers on Opera Omnia. What is their progress? Because 2 world wars and dearth of fund, everything, the thing progressed very slowly later on. 2015, I think 70 volumes have been published. Only 2 volumes are still remaining. That is on application of perturbation theory in astronomy. Then 1967, Swiss Academy and Russian Academy, they started editing correspondence of Euler. They decided that we need 6 volumes of 3,000 correspondence, out of which 1,000 was written by Euler. Mostly with famous contemporary mathematicians like D'Alembert, Bernoulli, Clairaut, and others, he wrote so much paper. Correspondence, there's letters. And mathematics, there are 29 volumes in Opera Omnia out of 70 volumes which have been published. Mechanics and astronomy, 31 volumes. Physics and miscellaneous, 12 volumes. That shows the quantity of work. Actually, more than 250 papers were published after death of Euler. Euler's papers continued to be published even 50 years after his death. In fact, he said it will require 20 years to publish all my papers after my death. That was a very optimistic approximation. It took 50 years. In fact, he wrote papers so fast and kept it on his drawer that academic press people will come and take the papers from the top, and the bottom papers are still not published. So it was very difficult to understand the top papers because they refer to the papers which are standing at the bottom of the file and yet to be published. In 1775, this 1 year alone, remember, he was totally blind in 1771. He published 50 papers. You know, there is a dictionary of Wolfram, which is called Math World. Just like, you know, you put some names, you can enter and find how many entries are there. So Euler, if you give in that Math World, you get 96 entries against Euler. And Gauss 70, Cauchy 33. Now let us do a little bit of samples of Euler's mathematics. We will not go into the details, but we will only emphasize the starting point. How startling the starting point is. The statement of the problem is very simple. We all will be able to understand. But it is the starting point to solve that problem. We start with one which is not mathematics, which is more of computation. You know, there are a class of numbers which is called friendly numbers or amicable numbers, like 220 and 284. Greeks knew this number. They said these are friendly numbers because if you take the divisors of 220, which are 1, 2, 4, 5, up to 110, and if you add these divisors of 220, you get 284. And if you take the divisors of 284, and if you add them, you get 220. So the divisors of 220 add to 284, divisors of 284 add to 220. So they are called friendly numbers. In fact, Pythagoras was so amused, he defined friendship by a friend is one who is the other eye, such as 220 and 284. So that is the only pair of amicable numbers known to the Greek mathematicians. Even till Fermat's or Descartes' time, that is 17th century, no other pair of amicable numbers was known. So Fermat found in 1635 or 38 these two. These are again a pair of friendly numbers. If you add the divisors of this, it is sum is this, and if you take the sum of the divisors of this, it is this. As you know, Fermat and Descartes were very, competitive. They didn't like so much each other. So when Fermat found this, Descartes said, I must also find on another pair. So Descartes found a pair like this, 7-digit numbers. Because Fermat found a 5-digit, he found a 7-digit. These are the three amicable numbers or friendly numbers known to the European mathematicians. There are many rules for finding these friendly numbers found by Arab mathematicians, but that came to light only in the 20th century. One is that Thabit ibn Qurra. He showed that if A equal to this, B equal to this, and C equal to this, where X is an integer greater than 1, and if you can find values of X such that A, B, C are prime numbers, then these two numbers will be friendly numbers, 2 to the power XAB and 2 to the power XC. But he doesn't say how to find the values of X. You can go on trying. X equal to 2, 3, 4. You can go on trying, you will get. prime numbers. But for which values of x you will get friendly numbers, nobody knows, because these will not be prime. If you try x equal to 2, you will immediately get the Greek 220 and 284 in this. Now see what Euler did. There are only 3 so far known. And in 1750, Euler gave 57 new friendly or amicable numbers. In 1747 paper, he listed 30. Then 3 years later, he added 27 more. This is from his 1747 paper. The first 2 are the Greek. Second one is Fermat's. Third one is Descartes. And there are 27 more friendly numbers listed. So he could compute all this. There is no computer. All this in his head. And the way he expressed this, it looks he found some formula like that Thabit ibn Qurra type formula he got for friendly numbers. This is the problem I'm discussing, because this made Euler the best mathematician in Europe, declared as the best mathematician. We have already seen that 1 plus half plus 1/3 plus 1/4, that sum does not converge. But if instead of reciprocal of the numbers, if I take the square of the numbers, it was shown in 17th century by Italian mathematician Mengoli that it converges. But converges to what value? That was unable. Nobody could get. Even Wallis, Leibniz, Jacob and John Bernoulli, 2 Bernoulli brothers failed. And Euler 1735 gave initial method and then later on gave 4 other methods to find this sum as pi square by 6. And where is the connection between 1, 2, 3 all the way up to infinity and pi, which is the ratio of the circumference by diameter? And this is mathematics, that this is gets related to pi square by 6. And how Euler did it first, as I said, the starting point of Euler is, okay, this the convergence that it converges, this proof I omit. For s greater than 1, it converges. So Euler started with the sine series. We all know the sine x. X minus x cube by factorial 3, x5 by factorial 5, minus x7 by factorial 7, and so on. So you divide by x. You get 1 minus x square by 6 plus x4 by 120 minus x6 by this. You put y equal to x square. So this is this. And this is sine x by x. So Euler treats this infinite series as a polynomial in y. And you see the right hand side, if it is 0, then we can easily see right hand side is 0 for x equal to n pi. 1, 2, 3. For all values of n pi, n equal to 1, 2, 3, this right hand side is 0. So this polynomial equation, the reciprocal, sum of the reciprocal of all the roots is covered by 1 by 6. So what it does, roots are n square by pi square. So the sum of the reciprocals by 1 by n square by pi square is equal to 1 by 6. So 1 by n square is pi square by 6. This is n square pi square. So pi square goes on that side, it becomes this. So zeta 2, this is the Euler's, famous equation. Euler being Euler, he did so much of mathematics others could not cope with. Doing this, he could have rested for entire life. But later on, he went up to 26 power and always found it is pi to the power same power. Zeta 4 pi to the power 4, zeta 26 pi to the power 26, and look at these coefficients. It is only possible for Euler. And he did lots of other things. It is alternating and cubes. Alternating to the power 5. These are again pi cube, pi 5. And this is the ultimate triumph in 1750. He did it for all even values of the power. Okay. Now, again, another starting point of Euler, I would say. There is something called Eratosthenes sieve to sieve out the prime numbers. This is very simple. You write all the numbers, then start with 2 and strike out all the multiples of 2. So strike out 4, 6, 8, 10, 12, 14, like that. Then you start with 3 and strike out all the multiples of 3, say 9, 15, 21 like this. So you get this. All the prime numbers are sieved out. Up to 23, all the prime numbers have come here. And then when you start with multiple of 5, this goes. So this is known as Eratosthenes sieve. This is a very simple child's play, it looks like. But at the hand of Euler, this takes enormous, power. Let us see why. Using exactly the same technique, Euler correlated a series with all the numbers, integer numbers, and all the prime numbers. Euler's formula connecting all natural numbers and prime numbers. What he did, zeta s, which he wrote earlier, for s equal to 2, he calculated this. So zeta s he writes like this. Then he multiply both sides by 1 by 2 to the power s. So this becomes 1 by 2 to the power s, 1 by 4 to the power s, 1 by 3 to the power 6 to the power s. Then you subtract. If you subtract, 1 by 2 to the power s cancels with this, 1 by 4 to the power cancels with this, 1 by 6 to the power cancels with this. So you get 1 minus 1 by 2 to the power n through zeta s, all multiples of 2's are gone. Then you multiply this by 1 by 3 to the power x. So you get 1 by 3, 1 by 5, 1 by 21, 1 by 27, all this, and then subtract from the previous one. You get 1 minus 1 subtracted from the previous line, all the multiples of 3 are gone. So this way, all the prime numbers are collected on the left hand side, and right hand side everything goes, only 1 remains. So you get this. This is the product of carried over all the prime numbers, and this is the sum carried over all the integers. 1 by n to the power s, this, and this is known as golden key. This is where Riemann zeta function started, and all the Riemann hypothesis and everything. A very enormous amount of maths have been created from this particular formula. Of course, Riemann expanded this s to complex number. For Riemann, s was not integers 1, 2, 3, 4 like that. It was complex number. Now, Euler, even at that late in the history of mathematics, could write 4 volumes of geometry. In Opera Omnia, there are 4 volumes of geometry. One thought there is nothing left in the geometry to be done during Euler's time. In fact, there is something called Euler Line. This is the most famous. In any triangle, the orthocenter, the centroid, and the circumcenter are collinear. These 3 points are collinear with EF equal to 2FH. E is the orthocenter, F is the centroid, and H is the circumcenter. E, F, and H are collinear. E is the orthocenter, point of intersection of the normals from the vertices. F is the intersection of the medians, and H is the circumcenter, that is intersection of the perpendicular bisectors. This is circumcenter, this is orthocenter, this is median, and E, F, and H, these 3 points are collinear, and that is known as Euler line. And this is, if this is D, then this is 2D. This is true for any triangle. Now, Euler algebra, the fundamental theorem of algebra is what we use every day, that all polynomials must have either real root or complex conjugate root, which during Euler's time it was not known. It was proved by Gauss in his PhD thesis. So, but they conjectured that all polynomials with real coefficients can be factored into linear and quadratic factors. But nobody could prove it during Euler's time. But whenever you have a conjecture, either you prove it, or the best way is to find a counter example. If there is only one counter example, there is no need to disprove it. It is gone forever. So Nicholas Bernoulli thought he has killed this conjecture, fundamental theorem of algebra. He has killed, because he said, I challenge everybody to factor this 4th order polynomial into either linear or quadratic. Obviously, it is not simple, because Bernoulli was a mathematician of some repute, But Euler somehow had the hunch that fundamental theorem of algebra is correct. So it must be possible to factor this. Don't try this. This is not a factorization of class 7. It will take you 7 to 8 printed pages, but it is only Euler who could do this. That he proved that these are the quadratic factors. These nested radicals must be frightening. But if you have the patience to carry out this multiplication, you multiply this by this, you will get this. Now again another starting point. Here again I will not get into the details, time is also less. I will just say, look at the problem and look at the starting point. In 1740, Philippe Noyde, a French mathematician who was quite senior to Euler, about 26 years senior to Euler, he brought to the attention of Euler that the distinct partition and odd partitions of several numbers are same. Can it be proved in general? Euler was having some serious eye problems, still gave the proof by the return mail and said, sorry, I took a little longer because my eyes were creating problem. But though he replied almost within 1 or 2 months. What is this? What does it mean? Partition means, suppose partitioning of 5. That means how 5 can be written in different ways using smaller numbers as sum. 4 plus 1 is 5, 3 plus 2 is 5. There is no other way I can write it. Forget about the order. 4 plus 1 is same as 1 plus 4. 3 plus 2 is same as 2 plus 3. So this is called distinct partitioning. All are distinct. No number is used more than once. So distinct partitioning of 5 is 3. And odd partitioning is that 5 I will write using only odd numbers. Here I can repeat, but I can use only odd numbers. So I can write 5, 3 plus 1 plus 1, and 1 plus 1 plus 1 plus 1 plus 1. So there are both are 3. Let us see for 8. For the number 8, how many distinct partition? 8, 7 plus 1, 6 plus 2, 5 plus 3, 5 plus 2 plus 1, 4 plus 3 plus 1. I think there it ends. So distinct partitioning of 8 is 6 and odd partitioning is 6. 7 plus 1, 5 plus 3, 5 plus 1 plus 1 and all that, 3 plus 3 plus 1 plus 1, 3 plus 5 ones and 8 ones. So they again 6. So that Philippe Noyde tried with lots of numbers and found this is always true. Then he asked Euler to prove it in general. And look at the starting point of Euler, because that gave rise to a fantastic method for the rest of the history of mathematics, that partitioning of number is connected to product of binomials. So here is to prove dn is on for all values of n. So Euler considered this product of algebraic polynomials, 1 plus x into 1 plus x square, it's like this. And if you multiply, you see this, 1 plus x plus this comes this. Then if you multiply this with this, you get this, and you look at the powers. This is what it is. You see, these are nothing but the distinct partitioning of 2, distinct partitioning of 3, distinct partitioning of 4. 4 can be only 4 or 3 plus 1. 5 we had 3. So coefficients of x to the power 5 is d5. So this p is 1 plus dn x to the power n, where n goes from 1 to infinity. This is the Euler's magic, that he starts from this and connects this with the distinct partitioning. Then odd partitioning, that also you could connect by considering this infinite product. 1 by 1 minus x, 1 by 1 minus x cube, these are all odd numbers. So 1 by 1 minus x, this is this infinite series. 1 plus x square plus x cube and so on. And this will be obviously x cube plus x6 plus x9. This will be x5 into x10, x15 and so on. And if you carry out this product, you will see this is what is happening. And you are getting the odd partitioning. Q is this. And this is the odd partitioning of 5. If you remember, 5, 3 plus 1 plus 1 and 5 ones. This is odd partitioning of 3. This is odd partitioning of 4. So Q is this. So P is this, Q is this. So if he can prove P and Q are same, then ON will be Dn for all values of M. And how does he prove Q is same as P? he writes P as this 1 plus x, then multiply top and bottom. 1 plus x square multiply top and bottom 1 minus x square. This multiply top and bottom 1 minus x cube. Then you see this product cancels with this product. This only remains. This 1 plus x square into 1 minus x square will cancel with 1 by 1 minus x to the power 4, which will come here. So you will remain with this. So P is same as Q. So Euler proved. In the combinatorics, Euler gave a method by posing a problem. This is a very nice history about this problem, that he solved it in 1789. But it was published only in 1811. That is almost more than 25 years after Euler's death. And he introduced in the combinatorics problem the recurrence relation. What is the problem? Problem is interesting. There are k number of different letters and have k number of designated envelopes. So you ask your secretary to put letters in the envelope, and she wants to mess it up. How many different ways she can mess it up so that no letter is in its correct envelope? K number of letters with corresponding k number of envelopes. How many different ways you can mess up so that no letter is in its correct envelope? Euler posed this problem and solved it by a recurrence relation. And then onward, this recurrence relation has become a powerful method in the whole field of combinatorics. It is very simple. Let the number be nk. The number of ways you can mess up. That is nk, where there are k letters. So it is obvious n of 1, if there is only one letter and one envelope, you cannot mess up. Number of ways of messing up is 0. And there are 2 letters and 2 envelopes, you can mess it up only one way. First letter in the second envelope, second letter in the first envelope. So n2 is 1. Now what Euler does, he says, okay, in case of k, I do it this way. We put L1, letter 1 in envelope 2 and consider 2 options. One is L2 is put in E1. L1 is put in E2. L2 is put in E1. Letter 2 in envelope 1. So they are messed up. So you have to mess up the rest in k minus 2 letters. And if you do not put L2, not put in E1, then you have to mess up k minus 1, because L2 should not be in E1, L3 should not be in E3, L4 should not be in E4. So k minus 1 letters have to be messed up. So he writes in 1, k minus 2 letters and envelopes have to be messed up. So it can be done is n k minus 2 ways. And in 2, k minus 1 letters and envelope have to be messed up. So it can be done in n k minus 1 ways. So with L1 in E2, total ways of messing up is this plus this. But L1 could have been in E3, E4, E5. L1 could have been in k minus different envelopes. So nk is k minus 1 into this. So we get a recurrence relation. You see, k minus 1, k minus 2, and k. So if I know the result for n1 is 0, n2 is 1, so I can easily find n3. n3 is 2 into n1 plus n2. So you get n3 equal to 2. Similarly, n4 is 4 minus 1, 3 times n2 plus n3. n2 plus n3 is 3, and 3 times 3 is 9. So that way I can proceed n6, n7 and all that. But Euler being Euler doesn't stop there. He generalizes it not step by step, directly goes into k. That details I omit. Only thing, the final result I give, that nk is given by this. You need not go gradually, step by step. You can directly go to any value of k. And if you take k equal to very large, k tends to infinity, it is very easily shown that nk with k, this tends to 1 upon e. Thus, with increasing value of k, the probability of perfect messing up tends to 1 upon e. That means more than 30% times you can mess it up. Even if you put all the letters in the envelopes randomly, more than 31 upon E is more than 0.3. So more than 30% times you can mess up every letter. Now I come back, forget the mathematics. Why Euler, the most famous mathematician in mechanical engineering, we should discuss. Because I'm sure all of you remember that Euler's equation for rigid body rotation, that was Euler's. Euler's buckling formula, we all knew, we studied in strength of materials. In fluid mechanics, his name is everywhere, starting from the Eulerian description and Lagrangian description. In turbine compressor, there is Euler equation. In fact, Euler can be discussed even in marine engineering or naval architecture. Because in 1727, Euler got the Paris Academy first prize for the first time in his life by solving the problem of optimum masting of ships. The Academy posed a problem, how many masts should be put and what to put in a ship. Because, nautical sciences are important, navigation is important for all Europeans. They have to conquer the world. So the question that was raised in a ship, how many masts we should put and what to put. So Euler solution came out as the first prize, got the best prize. Not only that, he did a lot of other work in nautical topics. He proved the impossibility of a perpetual motion ship proposed by Jacob Bernoulli. The Daniel Bernoulli's uncle, elder brother of John Bernoulli, he in a paper proposed a perpetual motion ship, which Euler showed it is not possible because it is perpetual motion. Because even thermodynamics idea was also not clear those days. It was all very hazy. But Euler even proposed using wave energy to propel a ship. He had considered a ship where waves are, flowing over the decks and getting collected in a trough. And from the trough, the water will drain out and propel the ship. There was for practical difficulties, it was not possible to make such a ship, but exactly the same idea is now fruitfully used in extracting wave energy for electrical power generation. In fact, Euler wrote 2 books and 12 papers on nautical sciences. So not only in mechanical engineering, we could have discussed him even in marine engineering. As I said, in St. Petersburg Academy, he was initially professor of physiology, so he had to work on the blood flow. He got the chair of mathematics only after his friend Nicholas Bernoulli died by drowning. Now, just to end the lecture, you must say, Euler the pioneer was also human. So Euler made a lot of mistakes. It is not that he did everything correct. He did a lot of things, most of which are correct, but even Euler made very simple mistakes. For example, just like other geniuses, Fermat and Descartes, Euler also missed 2 very small friendly numbers, 1184 and 1210. These 2 small friendly numbers were found by a 16-year-old student. What I'm trying to emphasize, that science is not a bhakti cult. That Euler is Euler, we cannot find any mistake in him. But science only progresses by finding mistakes of the greats. For example, Euler, he did so much of complex number. At one place, he wrote square root of -4 into square root of -1 is square root of 4, minus plus, so it is 2. But even now, a class 8 or 9 student will know this is not 2, this is -2. Because this is 2i and this is I. So product is 2i square, it is -2. Like Euler, he proved the special case of Fermat's last theorem. X cube plus y cube cannot be equal to z cube for x, y, z integers. Fermat said it for any n, but Euler proved it at least for 3, it is true. So after finding this, Euler conjectured that I can generalize it, that not only x cube plus y cube, not only z cube, a1 to the power 4, a2 to the power 4 plus a3 to the power 4 cannot be a4 to the power 4. Or to the power 5 to the power 5 to the power 5 cannot be to the power 5. This is 1 less than the power, the number of terms is 1 less than the power. This Euler thought this must be correct. And Euler died with that glory. Nobody knew whether it is true or not. It is a conjecture. Nobody was either to find a proof or disproof. But only when computer came in 1966, one of the shortest paper in mathematics reported this. 27 to the power 5, 84 to the power 110 to the power 5, 133 to the power 5 is 144 to the power 5. So Euler's conjecture is wrong. Nothing else needs to be written. Just one line paper. But with computer, obviously people will not stop. They found how about 4? Yes, 4 also they found a counter example. Later on, I don't remember the year, somebody found the smaller numbers, another counter example. Now, problem in statics, we all know Euler buckling. Euler assumed that, if I compress a, what you call column, then not only the vertical position is in equilibrium, a nearby position can be in equilibrium for some values of P. If P exceeds a particular value, a nearby position can be also equilibrium. That means equilibrium becomes neutrally stable. So from stability to instability, according to Euler, it goes from through neutral stability, because this was a simple idea. This bar is stable, this bar is unstable. But as you move the hinge point, right in the middle, this is neutrally stable. It can take any position. So Euler said the same thing here. From stability to instability, it goes via neutral stability. But now we know there is snap buckling, there is so many arch buckling and so many other types of buckling which does not go through the neutral stability. Equilibrium can be lost various ways. In fact, this was Euler's formula, we know great. You see, for this free body diagram of the column, bent column, there is no horizontal force. There is vertical force, loading, and bending moment, shear force, and the axial force. This is correct. But then Euler considered this problem. This is what I said, that after P becomes more than this, there is a pitchfork bifurcation. The vertical position becomes unstable, and 2 new equilibrium positions come on the left or on the right. Now, buckling of a pin-pin column due to self-weight. Euler made a simple mistake and concluded there won't be buckling due to self-weight. But Euler being Euler, his intuition told him he was wrong. So after a few months, he corrected his own paper and found, yes, due to self-weight also, a column can buckle. There was some calculation mistake which was corrected by a Russian much later in 1850s. And you know the mistake Euler made? He forgot to take this horizontal force in the free body diagram. Because now the weight is here. So to balance the moment, you must have n and n. Otherwise, this cannot be in equilibrium. And you said a displaced position will be in equilibrium, neutral equilibrium. This was such a simple mistake which Euler made, that a free body diagram was not balanced with moment. Well, I think now comes the most coveted slide in any lecture. Thank you.
Thank you, sir. Thank you. What a nice, what I will say, wonderful derivation, sir. This is the same thing we have observed, that you have delivered the lecture with science, technology, history, as well as society. All these things is coming together in your lecture, sir. So what I will say again, you have repeated the same thing in amazing lecture, that now the house is open for question answer. If anybody has any question.
Hey Amit, no question. This is Bimanda. Ashok da, my name is Biman Ghosh. I'm an 81 alumnus, and just want to say thank you very, very much, sir. This is an amazing hour presence with you and Euler, and it's really, really. Can you hear me?
These two names together.
No,
Infinity and 5. Infinity and 5. Don't take these two names together.
You did the handholding for us to walk the path of Euler, taking us back to the 18th century and what has been done at that time. So it's an amazing lecture, and I'm incredibly indebted to you for walking us through this path. Thank you very much, sir.
Thank you.
I have one comment.
Yes.
Comment is that if this lecture is heard by a young person, will he lose all enthusiasm for becoming a mathematician?
No. It's a lovely lecture.
No.
Amit,
You're not getting it.
Ashok,
I'm saying after hearing what a mathematician Euler was, then whether any young person will think that, oh my God, it is so great, it is impossible for me to achieve
just
anything.
because I didn't pick up a mechanical engineering topic to give a lecture after him, now after hearing Euler's credentials, others will not take up mathematics.
now, Amitabh, it is like that. You see, if I am permitted to say a few words, Euler made our life difficult in a way that all our laws of this mechanics, applied mechanics, they were linear. Force proportional to the area and etc., pressure, everything. Now Euler came and he created a dangerous situation where the laws of physics is no more valid. Euler buckling. So there the mechanical engineering, the applied mechanics deviated from the standard path of physics. Fine. So far so good, fine. So now my friend, he says that he has chosen not a mechanical subject, but a mathematical subject. But I, as his listener, I am delighted that he has chosen this Euler. Now, why? I'll explain a little bit, if you kindly permit. That is, in our younger days, from 1970s to 1990s, we read Martin Gardner. Martin Gardner was a puzzle mathematics correspondent of Scientific American. And in his quest for, he has got 6 books, volumes on this kind of thing. So in his quest, he used to find various types of problems like number of paints, number of colors required to map, and the geography of 2 countries, and various kind of things like the problem of numbers. And here he compared, sometimes he called upon Srinivasa Ramanujam. Srinivasa Ramanujam, I find Mr. Euler is a much more prolific producer of various mathematical equations, identities. But so is our Srinivasan. Srinivasan, he also created this kind of relationship which a person has to go through why this happened. But this happened. So we, in our younger days, we were amazed at the study of this kind of problems with Martin Gardner in Scientific American. That was one of my reasons of buying Scientific American. From 1961 onwards till maybe about 30 years, I had all these Scientific Americans collected. It's a purchased documents, and I used to enjoy those write-ups. So here I am coming at the end of my discussion. I must thank my friend for kindly taking up a subject which to him he is saying that he doesn't understand engineering. He does understand engineering very much, but now that in the vein of not understanding engineering, he has taken up subject on mathematics. I am delighted and I enjoyed this lecture through and through. Thank you.
I think if Srinivasan would have, Ramanujam could have, I think, had a longer life also, till 80 years. In your opinion, could he also produce so much? Because they appear to have a same tendency. That means just getting the solution by hunch, not by a rigorous process.
Actually, that's what I mean. Ramanujan notebook, people are still trying to decipher. Ramanujan lost notebook, which has about 900 new results, some of which have been proved to be wrong, about 5%. Some which have been proved to be correct, and some are still struggling. When still you don't prove, you don't know whether it is correct or not.
But as I think Hardy said that it must be correct, otherwise how could he write it?
Right? How could you imagine it? But there are a few,
Well,
mistakes are there.
Amitabh, I have a point here. You see, how nature reacts. Think of the lady who died very recently. She was given, Shakuntala Devi, she was given the 40th root of a 14-figure number. She did it. How
No,
she
in
did it?
IIT Kanpur once she visited, and I think both Ashok was there, I was also there, and I think she was computing in a fantastic way, because IIT Kanpur Computer Science Department, they kept lots of problems, beforehand ready for her. But that is not known to us, that how she could do it, all those things.
That is the question I am putting here, Amitabh. That
Actually, Shakuntala Devi was not a mathematician. She was a human computer. But Ramanujan was a mathematician of the first rate. Ramanujan was just a computer.
And Euler is a
mathematician,
an engineer, and everything.
They created mathematics. There was no graph theory before Euler. There was no modified equation before Ramanujan. But Shakuntala Devi should not be put on the same pedestal, because she is definitely a human computer.
I drew this analogy just to show, like Ramanujan and Euler, how the solutions came to their mind. In Shakuntala Devi also.
December 22nd, I gave a talk in Jadavpur University Maths Department on Ramanujan. There precisely the same thing was said, that Ramanujan himself didn't know how he got the solution. So don't talk of others.
I think that is true for Euler also. That is true for Shakuntala Devi also.
Even Gauss, Littlewood, everybody said that mathematics is something special. Sometimes it comes by divine inspiration.
You have to accept the scope of divine inspiration here. Unfortunately, I do not have any other solution, sir.
So you mean that God exists, because Euler was there, that proves God exists.
Well, at a later day, Ashokda, may we request you to come to this audience and present us with the Ramanujam lecture that you had delivered at Jadavpur?
Yes. We'll appreciate that. It can be done in the same series, Centenary series.
Yeah.
Thank you.
Biman,
I was very conscious that mathematics people will try to throw stones at me. With Achyuta and Amitabha and you supporting so much, I'll be very happy to give a lecture on Ramanujan.
Oh, delighted.
Of course, I'll pull a few more volunteers in Amit Rai Chaudhuri, Sujay Mukherjee, etc. They are all my known friends.
Thank you, Vivanda, for your presence.
Pleasure, sir.
Sir, may I ask something?
Yes.
Sir, you said the recurrent relationship was discovered using that later.
No, in combinatorics. In combinatorics, recurrence relationship was known. But to apply that in combinatorics problem, instead of NCR, NPR, that kind of formula, factorial, this thing, that thing, normally combinatorics problem are solved that way.
I heard a lecture by Professor Manjul Bhargav. There he said that this Fibonacci series was discovered by Indians much before, like by Hemachandra. So they don't use this rabbit and then population problem.
I know Hemachandra series. I know Hemachandra. That was from. He was a linguist actually. He was a poet and linguist, and he talks of bits, rhythms and bits.
Logu and Guru bit. So that is
right. There is one line formula only. Hemachandra series is just one line formula.
So
there is a little difference between Fibonacci and Hemachandra.
So I saw a similarity here. That is why I asked that question. Thank you.
Can I ask something?
Yes.
Sir, Sum of
introduce
the
yourself.
powers of a number, you have said.
Please introduce yourself, Master.
Hello?
Before questioning, please introduce yourself.
Yes, sir, sure. Sir, I am Vaibhav from Thermal Engineering, sir. MTech, Thermal Engineering. Sir, you explained about the powers of some of the powers of the numbers which were calculated, right? Sir, I've read about Diophantine numbers. Are they related to those? Sir, you are mute, sir.
Sir, kindly unmute,
So
sir.
you need to unmute.
Sir, kindly unmute, sir.
Okay. No, Diophantine equations are equations where the variables are integers, not real numbers. That is called Diophantine equation. That like p square minus 2q square equal to 1. Can you find all the integer values of p and q? It's just 3 and 2, right? One solution. 3 square minus 2 into 2 square is 1. You can say 17 square minus 2 into 12 square. Again, it will be 1. So P and Q, you are getting either 3 and 2 or 17 and 12, then 99 and 70, this kind of infinite solutions you can get. These are types of equations which are called Diophantine equations. Linear Diophantine equation is easy to solve, but this is the quadratic that I said. This is particular one is known as Brahmagupta's equation. Brahmagupta solved it 1,000 years before the Europeans. In fact, he challenged that anybody who can solve p square minus 92 q square equal to 1 within 1 year, I will accept him as the greatest mathematician. Because there the solution will be p equal to 1170 and q equal to 120, the first solution. Then higher solutions anybody can find. If you give me the least solution, infinite solutions I can easily obtain. Anybody can. So these equations are a different type. These are mostly in number theories.
Thank you, sir.
Okay, Amit, because you are not going to offer tea online, because you are not going to offer tea online at the end of the lecture.
But we can give you an online token of application.
I have two small duties, sir, here.
Yes.
Okay, please.
Yes.
Online
I would
token
request
application
the
for
session chair to kindly hand over the certificate of appreciation as well as a memento as a token of appreciation to our honored guest.
Yeah.
I'm taking it.
Hereby I am giving it to you. Please, sir, consider it.
We have a memento also. We'll be keeping it in the department. And sometime later, we will arrange to send it to sir.
So,
thank you.
Yeah, we are indeed delighted to host sir here.
Sir.
Thank you for presenting us
I must also thank
1 hour. Just 1 hour. That will
Euler did some
I must also thank the session chair.
Oh, no. Somebody has some question.
Hello, sir. My name is Bidayak. I am 2012 pass out of BE College. Euler did some phenomenal work in the field of calculus of relations.
Yes.
Amit, I think Ashok has been talking for more than an hour and he is not well. Therefore, I think please request the other members they can send the questions by email and they can be answered later. Otherwise, I feel little bit uncomfortable for Ashok.
Sir is not sure well health now, just now. For the time we want his fully recovered, and just all other those who are the listeners, I am requesting them if they have any question or doubt, please email him. Okay. So today we can stop here. Okay. Thank you.
Thank you.
Thank you again, sir. Thank you for his life.
I should also thank the session chair, Professor Roy Choudhury, for hosting the session, for leading the session. I must thank you. And it's really, I mean, we are indeed grateful and we are delighted to host this lecture series. Thank you very much. Yeah, I find a lot of people joining. I saw Bimanda joining here. I even saw Professor Devesh Bhattacharya also joining from there, from Auckland. So it's we are really.
Biman is not mechanical. Biman is from civil.
And what a
But
genius
still,
this.
Biman has taken interest. That's a great thing.
I graduated from metallurgy program.
Yes.
Oh, metallurgy. Yes, okay. Okay, Biman, I apologize.
No, thank you.
I apologize. But I cannot place you.
Dada,
Biman, when you talk, I cannot place you from which branch. You are multi-knowledgeable.
My humble submission, please, please don't say all those words.
No, Biman. I always learn from you. You are 20 years junior to me, but I confess, I learned from Biman's way of speaking, his way of demeanor, etc., etc. Thank you.
Let's call it a day for Ashokda and for our audience. We had a wonderful time. Let's call it a day. Thank you.
Right, Biman. What is the time with you now?
It's 8:23 in the morning.
Okay, but starting was rather difficult, but now it is okay. I hope you had your tea. Your tea.
Yeah.
Okay.
And
Thank
in
you.
Auckland, it's past midnight.
Yes. Hari Bapre. Is there somebody from Auckland Park?
Thank you very much.
Yes. Professor Devesh Bhattacharya was there.
Thank you, sir. Thank you very much.
Professor Bhattacharya joined from there.
Thank you,
Great.
sir.
We'll also be having Professor Bhattacharya speaking here in this forum next month.
Okay, right. Bye. Thank you. See
Well,
later.
thank you very much. With permission of you and with the permission of the session chair, I would now request our volunteers to close the session down. So, thank you very much. We really had a wonderful time.
Thank you, sir. Thank you very much.